Our next speaker is Niranjan. Niranjan is pursuing a PhD in 202 group at Chalmers Institute of Technology in Sweden. His PhD focuses on continuous variable quantum computing using superconducting qubits. He did his master's in physics and quantum technology from University of Cologne, Germany, and thereafter completed his master's from 202 group at Chalmers Institute of Technology. His master's thesis focused on high-quality planar lumped element superconducting resonator. Okay. So with this, I would like to invite Niranjan for his talk on universal control of bosonic modes via asymmetrically threaded squids. Niranjan, could you please share your screen?
Yes, sharing my screen now.
Okay. Yeah, I can see your screen now.
Yes.
Thanks, Niranjan, and you can take over from here.
Yeah, thank you for this opportunity. So I'm working on getting universal control for the bosonic modes, and I specifically work on superconducting qubits. And as you know, people use Josephson junctions. I use a configuration of them called asymmetrically threaded squids. There is a lot of jargons in my title, but I will explain you at the end of meeting. You'll be familiar with those things. Let's start with one of them called bosonic modes. What is a bosonic mode? That's an interesting question. To answer what is a bosonic mode, let's answer what is a conventional qubit in the first place. So usually you would have seen people going the other way, but yeah, for this talk, this is necessary. A conventional qubit takes a linear oscillator, it could be a harmonic oscillator, and then adds a nonlinear element to it. Usually in superconducting circuit, we take a LC oscillator and then replace the inductor to a Josephson junction to form a qubit. This creates an effect in its potential. So now an harmonic potential due to this nonlinearity becomes an anharmonic potential. That is, the energy levels are not equally spaced anymore. Because of this, we can isolate the lowest most two-level systems, 0 and 1, and sometimes 0, 1, and 2, depending upon the criteria, and we call them a qubit. To be called as a qubit, familiar story, it needs to be able to do entanglement and superposition, right? This is already shown in various papers, and people have done it quite sometimes, and the humanities are very familiar with this thing. But quite recently, people have started to use another way to achieve the same thing called a bosonic mode. Instead of having a nonlinear element, you take a linear resonator, that is basically a harmonic oscillator, which is an LC circuit, and try to encode the information in it. So to understand what is a harmonic oscillator, in simple terms, they have quantized energy levels which are equally spaced. That means the transition frequency between 0, 1 and 1, 2 are almost are equal. Sorry. With this such a system, we can create a logically encoded qubit on it, and such a qubit, one of such implementation is a cat qubit. You take a coherent state or superposition of two coherent states, and then depending upon their phase, you encode it to be 0 and 1. This sort of encoding is called a cat qubit. This state is called a cat state, and this sort of encoding is a cat qubit. The point I want to emphasize is, at least in theory, we want to utilize as many as energy levels as possible. And in a harmonic oscillator, there are infinite dimensional Hilbert space. So that means we can use essentially infinite energy levels. In reality, we would truncate to some 30, 40 energy levels, and sometimes people have gone up to 100 energy levels, but that is not the scope of this presentation. So in short, a bosonic mode is a logically encoded qubit on a harmonic oscillator. To achieve such a bosonic mode, to achieve a universal control over such a harmonic oscillator or a logically encoded qubit on a harmonic oscillator, we want some certain things. So we know there exists Bloch's sphere, A universal control means you should be able to access every part of this block sphere. So you should have a gate set that takes you from point A to point B anywhere on this block sphere, right? To have such a system, we want to understand Gaussian and non-Gaussian operations in terms of bosonic modes. Bosonic modes are, in other words, it's called as continuous variables. They are your quadratures, position and momentum. If you talk in terms of photonics, here also it same translates the same way up to some constants. Let's stick to that notation. Now we take a harmonic oscillator and see its position and momentum states and plot a Wigner space, Wigner probability function there. And in the Wigner space, you see a vacuum state to be like a blob, a Gaussian standing there, right? So you can do certain operations, like you can populate the harmonic oscillator, which is basically displacing that particular vacuum state to state 1, 2, 3, and so forth. And similarly, you can take the vacuum state and squeeze it. That means you take the uncertainty from one part of the quadrature and move it to the another quadrature. The point I want to emphasize here is all these operations are still Gaussian. That is, there is no Wigner negativity, which means still, if you want to create a quantum state, you want to have a Wigner negativity. So these systems are being Gaussian. If you put up a scale here and see it, it would be a multidimensional Gaussian, but this is not enough to do a universal control. Then we want to achieve some sort of non-Gaussian operation, right? To do so, there are papers which suggest we can get a state like a cubic phase state. This state is called a cubic phase state, and the operations used to perform this are cubic phase gate. Once you have those sort of systems, then it is shown that you can have a universal control of such a bosonic mode. You can do any sort of encoding. It could be cat code, binomial code, and so on. But to do that, you need to have a Wigner negativity, and Wigner negativity is given by such a gate. All right, this is the basic theory. Let's see how to do it experimentally. What do we want? We want a linear cavity to store bosonic modes. Why it needs to be linear? As I said, if it's linear, then the energy levels are equally spaced. So we want such a system, right? And then we want a native on-demand nonlinear operation. That means you need to do some sort of nonlinear operations like a 3 omega tone or a cubic gate, which gives you non-Gaussianity. But at the same time, you should be able to do it on demand. Like you should be able to send it a pulse there and this operation turns on and off. In case of Josephson junctions, if you see, there is always an harmonicity turned on. So you need to do some magic with Josephson junctions still to achieve this. And here comes the asymmetrically threaded squids, also known as ATS. We take a set of Josephson junctions. Here, X represents a Josephson junction, and we arrange it into 3 arms such that we form 2 loops. So these junctions have certain energy EJ and EL and ER, and they are shunted by a capacitor C. Now, if it's a qubit, there will be 1 junction. If it's a flex tunable qubit, there will be 2 junctions. Now there is 2 loops here. That means you can still flex tune it via 2 flexes. That is phi L and phi R. Meaning you can send magnetic field phi L and phi R into these loops, and the potential of this ATS will change. That's what this equation says. And note that the phi L and phi R for the simplicity has been transformed to phi minus and phi plus coordinates. The point I want to emphasize is to look into this Hamiltonian. There is some linear paths. There is some interaction terms GI, which is being driven at particular frequency, right? So what it exactly means is if you have such a term A dagger A in the Hamiltonian, experimentalists to right away see it, we should drive this particular system to the ith frequency or I times that particular frequency. That means, let's say I have a qubit at 5 gigahertz or ATS mode at 5 gigahertz. Then if I want to turn on my displacement, I will drive it at 5 gigahertz. If I want to squeeze it, I will drive it at 2 times of my 5 gigahertz, which is 10 gigahertz. If I want to try squeeze it, I will drive it at 15 gigahertz and so on. And you see there are AC terms and DC terms. Note that why this AC DC comes, because we want to flex tune it. flux is applied to a circuit by applying current to it. So this DC term is basically a static DC current there. You just keep the current turned on always. But this AC part is like an RF part that creates your on and off on demand interactions. One can notice that the DC is always turned on. That means this A dagger A raised to the power 3 is always turned on interaction in our ATS, which we don't want, right? So we want an interaction which can be controlled. So somehow we need to get this G3 DC turned off. Not only that, if we expand this Hamiltonian, this keeps on going like G4 is there, G5 is there, and so on. So there are G4 DC terms, G5 DC terms, G6 DC terms, and all this together could make our ATS look very non-linear. But we want a linear cavity. So what we can do, if I plot this flux space, that is, we take the phi L and phi R and plot them for different parameters like the ATS resonance frequency and what is our G3 and what is the care. Care is basically G4 and so on. We happen to see there is a region where the care and G3 DC goes to 0, which is what we want, right? So DC is always on term and care is again G4, which is an always on term. The beauty of the ATS device is that not only G4, but all higher order odd terms also goes to 0. So the first always on nonlinearity in such a circuit is 6th order interaction, which is highly which is a very weak interaction. With this, we can approximate our ATS to be a linear system with on-demand nonlinearity. How we do it by on-demand? Again, remember that we drive the AC pulses for driving particular gates. So my device looks like this in the lab. So we fabricate a device on aluminum on top of silicon, and we have a big capacitor here. This big capacitor corresponds to this capacitance C, that is the shunting capacitor. And we have a qubit which is dispersively coupled to such a ATS device. Why we want a qubit? Because it is dispersively coupled to the ATS, our qubit shifts in frequency depending upon the population of the ATS. And thus we can use this as a control and readout system for reading the ATS device. And again, there is a resonator coupled to the qubit, same story, dispersive coupling. So you are dispersively coupled to a qubit to the resonator. So whenever qubit population changes, resonator population changes. We can use this qubit resonator system to do Wigner tomography on our ATS device as well. Okay, so with that, I can tell you we can have tri-squeezing and 2 omega tone, 1 omega tone. If I go back few slides, you see all we want is a 3 omega tone, 2 omega tone, and a omega tone, which we can turn on demand to get such a cubic phase state. That means the ATS device is proved to have a universal control of bosonic modes. Okay. Oh, sorry. Not only that, we can do even.
Hi, Niranjan. I think you unshared your screen. Could you please reshare?
Okay. Yeah. Sorry.
Yeah. Thank you.
Yeah. So we know that we can make cubic phase gate with the ATS device, but we can do even much more beautiful things with this ATS. The current experiment that we are doing with this lab is we have a multi-mode chip, which is basically having 4 cavities, which is labeled in pink color here. And then there are 4 resonators, which are green in color, or sorry, transmon, which are green in color, and a resonator, which is blue in color. The previous image here shows 1 resonator, 1 qubit and 1 ATS device, but here we don't have an ATS on the cavity, but as a separate coupler. This enables us to do beam splitting between these cavities. That is, it's same like a coupler in a 2 qubit chip. So now we have 2 cavities, which can be used as a linear system. So you can do a linear like a cat qubit code there, but then still use this ATS to beam splitting between these two cavities and so on. We can also use this ATS to do beam splitting on cavity 1 and 2, depending on the state of the cavity 3. So it could also be a controlled beam splitting gates. We are trying to achieve that actively in our lab. And once we are able to do that, we'll be able to do something called a boson sampling. And this is something a classical computer cannot do efficiently. So if you are able to show that our current chip is can be successfully do boson sampling, that means this has quantum advantage over a classical computer. For you guys, this is how the current device looks. And the small spider-like structure here is the ATS device. And there is a 4 cavities, which is a LC oscillator. You could see the C part capacitance is the big circle-like structure, and the inductance is the meandering here. And there are 4 qubits, 1, 2, 3, 4 for a readout system, and 4 readout resonators, and so on. Yeah, so this is where my presentation ends. I hope you like it. And there are a few references here. The idea of getting a universal gate set comes from this paper, and people from Alice and Bob, different companies, already uses ATS to show that we can have a cat qubit which has a bit flit times exceeding 10 seconds. So this is something interesting to me. I hope it is also interesting to you.
Thank you, Niranjan, for this wonderful talk.
Yep.
Now we would like to proceed with some questions. I believe we have some. So Munib asks, Josephson junction induces non-linearity, but for bosonic states you need linearity, which is eventually possible when you have simple harmonic oscillator. Why do you need non-linearity?
Okay, so to answer this question, we need to go back to this particular slide. See, we are trying to get a non-Gaussian operation. The non-Gaussian why we need non-Gaussian operation? Then only we can have a Wigner negative state, which enables us to do bosonic computing. But to get this non-Gaussian operation, a linear mode cannot do it. A linear mode can only have a displacement and squeezing, but to achieve non-Gaussian operation, you need some sort of non-linearity. And that is the reason why we have on-demand 3 omega tone. So the 3 omega tone here is what the non-linearity is.
And he also asks, does your lab support research in circuit quantum electrodynamics?
Yeah, we actively do that.
Okay. If you have any more questions, you can post it in the chat box, or you can ask them later on via email. So thank you once again, Niranjan, for this wonderful talk.